Great to see you here again. We finished the first session about prime numbers. What we're going to do now is to have a look at what is called the Sieve of Eratosthenes. It's a practical way how to find the prime numbers which are in fact within a specific range. And we will go through this sieve step by step to show you how this works. Now, finding primes below a specific number, it's in fact the thing that we want to know. We want to find the primes that are below a specific number, and we want to find them in an easy way. We already know that there is the rule that when we have a number n, that the largest prime number would be smaller than the square root of n. Now, when we look at square root of 50, we'll look at n being 50. We see that the square root of 50 is 7.07, which means that the numbers, let's say, up to 50 can either be divided by 2, 3, 5, and 7. They cannot be divided by larger numbers, but the thing is, when we look at the by larger primes, basically, what we see is that when the numbers that we cannot divide from 1 to 50, basically from 2 till 50, which cannot be divided by 2, 3, 5, and 7, they must be prime numbers. So basically, when we find these numbers, we can identify which are the numbers that are in the list. Now, basically, only 2, 3, 5, and 7 can be divided by themselves. So we can divide 2 by 2, 3 by 3, 5 by 5, and 7 by 7. So basically, we have to already exclude those prime numbers. Now, when we look at all the numbers divisible by 2 except 2, we have all the numbers from 1 till 50. I put 1 in gray, and we see that all the even numbers except 2, I color them in light blue, those are all the even numbers which are in this list. So it means that they are not prime because I can divide them by 2. Now, the next step is to look at the numbers completely stable with the numbers that are divisible by 3, except 3. Now, we see all those numbers are in the yellow cell. So we have 6. 6 was already divisible by 2, but 9 is a new number. We find 15, we find 21, 27, and so on. So we find a range of new numbers which cannot be which are divisible by 3. So we already have 2 and 3. Now we're looking at the numbers 5 and 7. And the numbers divisible by 5 and 7, except 5 and 7, are given by 5 by the underlined numbers. So we find some new numbers or some numbers which have not been in the previous list, like 25 and 35. And we also find a number, one number divisible by 7, which is 49. So basically, when we look at the sieve, we find that the result is basically given by all the numbers that have not been selected before. So we find the prime numbers 2, 3, 5, 7, 11, and so on, up to 47. So these are the prime numbers that we can identify between 1 and 50. And 1, of course, is always excluded. Now, this is important, and we can look at some properties of prime. And the first theorem related to prime states there are an infinite number of prime numbers. It means that we can keep on finding primes, and that quest has been going on for centuries, and mathematicians have developed different ways to identify primes. There are different ways to calculate them, and we will look at some prime numbers, some ways to find numbers that could be prime, but the problem is always that we have to prove that the number is prime. And for large numbers, this can become quite complicated. One of the elements, or what the formulas that's being used to find primes, is 2 to the power of p minus 1, in which p is a prime number. And we call the prime numbers that are called using the formula the Mersenne primes. Mersenne was a mathematician. He used this formula to calculate primes, and you can find primes with this formula quite easily. So we have p to the 2 to the square, first prime number is 2, 2 to the square minus 1 is 3, 2 to the third minus 1 is 7, so we already find 2 primes, but those are easy to find. 2 to the fifth we get 31, 2 to the seventh we get 127, but when we look at 2 to the 11th power, so this is the next prime number, we find the number 247, and we can easily prove that this is not a prime number. So not all the Mersenne numbers that we calculate are basically prime numbers. And when we go for larger prime numbers, what we get is that the calculation or the proof becomes more and more difficult, or basically time consuming. Now, what we see at this moment, there are about 51 Mersenne primes that have been found and proven. So people are still looking at finding more of those Mersenne primes, because it's a very interesting formula to find prime numbers. They're not all prime numbers, but a large number of them are basically prime number. Now, we find again, when we look at numbers of primes and an arithmetic progression, we look at the prime number theorem, we can say that the ratio of the number of primes not exceeding x and x divided by ln x approaches 1 as x grows without bounds. Now, ln x is the natural logarithm of x with base e. Now, based on this theorem, we can calculate the odds that a random selected number is prime, and that is in fact approximately equal to 1 divided by the natural logarithm of n. So when we select a number, we can have an idea what's the probability that that number will be prime. When we consider odd integers, we see also that we can make them a part of two types of arithmetic progressions. And we are looking at arithmetic progressions also to find prime numbers. Now, when we look at the two arithmetic progressions that we can make, it's 4k plus 1 and 4k plus 3. But what when we put here k as being primes? So when we look at 4k plus 1, we have 2 plus 1 is 9, is not let's say, a prime number, but let's say 3. 12 plus 1 is 13. We have 1, k can be 1, we have 5. For 2, we don't have a prime, it's not in this list. We see that for 2, we find 9, which is not a prime number. But when we have the others for 4k plus 1, we find prime numbers which correspond with this progression as 5, 13, 17, 29, 37, 41. And for 4k plus 3, we find 3, 7, 11, 19, 23, 31, and 43. Now, this is interesting to know that we can find prime numbers like this, but what happens when we have a progression? A times k plus b, with k, 1, 2, and no integer than larger than 1 divides both a and b. So a and b is in fact a possibility. So basically a and b are in fact primes, and we can use this progression and we find an infinite number of prime numbers. But we can say, are all of those basically prime numbers or not? So we have to be careful here, because we can find a number, but it's always important to prove if this is possible, yes or no. When there is not a real, let's say, a proof that we can find by logic, we may find a proof that we are just going to calculate all the numbers and find more and more numbers. But it's not always easy to have, let's say, a proof that is valid for all numbers. Now, what we have here is that in the next session, we will look at conjectures and open problems that are related to primes. These are very important because the conjectures give us a new insight in primes. And of course, there are a number of open problems that still exist, that have been defined, that people think or assume that they are correct, but a proof, a general proof, has never been given. So basically, the mathematicians may say, well, these conjectures or these open problems, we consider them for true up till now, until we can prove it, or when we find a counterproof. If we find a solution where it is not true, where the conjecture is not true, of course, we can say that the conjecture is not generally true. So you're doing a great job. I will be looking forward to seeing you in our next video. Thank you and bye-bye.